Hi, today we start chapter 4, which is about counting. That's actually part of mathematical discipline called combinatorics. And generally the idea here is just to count in how many ways can certain configuration occur under certain constraints. And today we will start with the most general rules, and they are product rule and addition rule, and they are the basis for all the other rules basically that we'll learn in this course. So let's make sure that we understand how these fairly simple rules work. So I will start with the product rule first. So that's the rule 4.1.1, it's here. Here, and 4.1.1 says if an operation consists of n steps and for I between 1 and 1, ith step could be performed in ki different ways, then the whole operation could be performed in k1 times k2 times kn, or in short version product called ki when I goes from one way. It's very important actually to recognize, so whenever we have something that's done in stages and then you assemble the whole thing from the stages without any restrictions, this is the product principle. One more thing, typical word for the product principle is and. Take this with little reservation. I'm not saying wherever you see and it's product, but generally very often you can recognize the word and inside those constructions. By the way, just addition rule, when we show it later, will be very often associated with the word or. Again, with restriction, don't take it literally, but I think it's a good hint. So let's do a couple of examples to see how this simple example works, and actually shows you why is this true. It's fairly obvious from the construction. So here it is, example 4.1.2. Peter is to choose a schedule by choosing one of 4 math courses and one of 3 science courses. In how many ways can he choose his schedule? Can he choose it? So there are 2 different ways how you can address this problem. They're both legitimate. I probably prefer the second one, but they're both good, and they can give us at least success on the exam. So key thing here is that there is a word and. So you see his operation of choosing a schedule has 2 stages. One, choose math, and no matter what you choose for math, you can choose one of the 3 physics courses. So generally, these are our K1 and K2, so our total count is, we can say the following, it's 4 times 3 schedules. So this is your K1, this is your K2, total is 12. I think that second way is also to visualize what's happening, so here it is. You have 4 options for math course. Math 1, Math 2, Math 3, and Math 4. Now each of them branches 3 different ways. Science 1, Science 2, Science 3. Science 1, Science 2, Science 3, science 1, science 2, science 3, science 1, science 2, science 3. Now, where are the schedules here? Schedules are complete branches. So what's this? Math 1 and science 1. So this node gives us 3 different schedules. First one. And then second one also gives us 3, and third one gives us 3, and fourth one gives us 3. So we have 4 times 3 schedules, and that explains this formula, and basically the same reasoning is for the general formula. Looks very simple, but it's not always this way. Why? Because our trees are not always this homogeneous. So sometimes they are ruined, they spread in different ways according to the rules. So generally you need to set up a problem properly, and then within the problem, if you have a chance to recognize one of those configurations, you call them. But you have to work out the problem and set it up on your own. So here's one example. Again, not too complicated, because the number of configurations is fairly small. So here it is, problem 413. Again, Peter, John and Peter. John and Peter play 7 games. Who's the winner? 3 wins in a row, or total of 4. 4 wins. And let's say that we already know that first was won by Peter, and second and third by John. Peter, John. In how many ways can the game continue? So generally what we know is the following. Our tree has the following: Peter on first, John on second, and John on third. And now what could happen? Generally, next game, it could be either John or Peter, you agree? If John finishes, whenever the game finishes, I'll put in the red circle. This is the end. John has 3 wins in a row. If Peter wins, then the game proceeds. So, so what could happen basically? So far in this version, everybody has 2 wins. So generally, whoever has 2 out of 3, because now it's just 3 games, so 3 games left. So the winner needs to win 2 more games. So what happens for Peter if he wins 2 games immediately? So or we can just do the branch. Peter, John, Peter, John, Peter, John. 6. So let's see. So this is 1, 2, 3, 4, 5. 6th game is decided. Is anything finished here? Yes, this is finished, because Peter has 3 in a row. All the others are, what happens here? Here they are equally distributed, 3, 3, so we have to continue playing. What happens here? Again, they are 3, 3, they need to keep playing. This one's finished because John has 4 wins. And then what happens? So far I have the 3 endings. And then if I continue on these 2, everybody has 3 wins, so whoever wins, so they play the 5th game, and it could be the Peter or John, game ends. So basically I just drew all the possible scenarios, and then I just do the count. 1, 2, 3, 4, 5, 6, 7, so 7 possible games. Here it is, or 7 possible scenarios. So here we had something completely opposite. We didn't use any formulas. Maybe toward the end we said, oh, 2 here, everybody's free. So this looked like homogeneous. but everything else was, you see how uneven this tree is. This branch completely stops because John heavily had the winds. Here we had the stop, and then these guys had the complete branching. But you see, you cannot call formulas here. You have to do individual counting and drawing. And basically our work in the whole chapter will be a combination of those two principles. Let me now talk about addition rule. Generally, addition rule tells us how to count elements of the union. So theorem 4.1.2. So suppose that A1, A2, AN are, and this is crucial, disjoint. If they are not, you'll see a little later we have to adjust the formula. Disjoint means they share no elements in common. And then, and let A be union of AIs when I goes from 1 to n, which is 1A1, union A2, union AN. By the way, here is where you see that OR, because union is OR. So OR is a physical word. Because element is in A, either through A1, through A2, or through AN. Also, you can think of it as cases. So here, they are not stages of the complete scenario. They are all complete scenarios, but with alternative. I can accomplish this way or that way. They are all complete accomplishments, and you don't assemble them at the end like in the first case. So that's the biggest distinction. So generally what? I didn't finish the theorem. That number of elements of A, which is cardinality, just you take account how many are in A1, how many A2, plus how many in AN. Generally what's happening, you are piling up the evidence. Evidence for A can go through A1, or through A2, or through AN, and that's exactly, you pile up all that evidence, and that's the evidence for A. So let's see how, one of the typical examples, please pay attention to the next one, because I asked that one quite often in different settings about the integers from certain interval. So what would that be? Example 415, it says the following. How many integers 1 to 999 do not have repeating digits? And number 2, how many integers (1 to 999) do have a repeating digit? So problem 1. I can think of it as doing 3 stages. So imagine I'm assembling, like, there are 3 boxes, and I need to fill them in. And then I will just assemble each of them and then see in how many ways can I assemble everything together. So here it is. Imagine I'm supposed to choose the first digit. First digit could be any number between 1 and 9. So I have 9 passes. So K1 is 9 ways. 9 options. What are they? 1 through 9. I cannot put 0 because 0 is never the front digit. Alright. And now imagine, doesn't matter which one I put. Let's say secretly I put 3, but we don't know. But doesn't matter whether you put 3 or 7 or 2, because 3 looks the same in all the cases. So no matter what I put 3, here it's 3. Then how many options do I have here? If I don't want repeating digits, I can do anything I want, except my secret number there, it's 3. But either it's 3 or 7, that's the only one. But I also have a gain, because 0 was disqualified, and now 0 is absolutely legitimate candidate. So generally what happens, I have 9 options again. Why? Anything between 0 and 9, except what I used in the front. And then here I have 8 options. Why? Because here I cannot use those 2 numbers that I already used, and now I can use anything else. So that's 8 options. And then what? Now I just multiply. 9 times 9 times 8. So the total is 9 times 9 times 8, which is 81 times 8, which is 648. But wait a minute. These are just 3-digit numbers. But here it says 1 to 999, so I cover the numbers all the way from 100 up. But I still need the 2-digit numbers and 1-digit numbers, so I have to repeat the same reasoning for the 2-digit numbers. So what happens? For 2-digit numbers, the same story. I cannot have 0 in front, so it's 9 ways. But then I can have 0 later on. I cannot only have the first one, the same reasoning, so that's 81. And finally, I can have 1-digit numbers, but who are they? I don't need combinatorics from 1 to 9, so 1-digit number, there are just 9 of them. And now, so here you can say, wait a minute, why am I showing you product principle while talking about addition principle? Because what? It says, that integer could be, this integer is either a 3-digit integer, or 2-digit integer, or a 1-digit integer. And they are disjoint, always check that. That could be very dangerous for your correct counting if you don't double check. No number is at the same time 3-digit and 2-digit, so these ORs are disjoint. So generally what? I just add up the evidence. So pile up the evidence. 648 answer. 648 plus 81 plus 9, which is 738, I would say. Did I get the same number? I hope I did. 738. Okay. Now in part 2, I can use complementary principles. Why? Because those that have repeating digit what's the opposite from repeating? No repeating. So generally what? Altogether, there are 999 numbers between 1 and 999. If you remove those that we already calculated, which is 738, the rest of the numbers do have repeating digits. So it's 261. And that's it. Very often we use that trick. We don't like it because those with repeating digits would be fairly tricky to count. So generally sometimes, always think if you need to count something, is it maybe better to count the complement and then subtract from the total. That's one of the standard tricks in counting. So here is the answer. By the way, let me just mention one alternative. If you don't like it, just forget it, but if you do, you can definitely use it. I could have, I thought maybe, but then here I would have 2 zeros, that would be, no, this is the way we do it. Right. So there is a variation of this addition rule that is called exclusion-inclusion principle. That one covers the case when they are not disjoint, when there are overlaps. And this is how it looks, theorem 413. Inclusion, exclusion, principle. And this one says the following: cardinality of A union B was the same thing as a minute ago. So you are taking a union or, but this time they might overlap. If that's the case, almost the same as a minute ago. You add up A, add up B, and you subtract the overlap. The reason is fairly simple. Why is that? Because look at this. If this is A and this is B, when you count A, that's green. So you count all of them. When you count the B, you report all the blue ones. Then what happened? Those guys in the overlap were reported twice. Once as blue, once as green. And should we report them? Yes, but only once. That's why one reporting should be removed. And there is also version for 3 sets. And that's next theorem 414. Let me just immediately put that theorem next to it. So 414 says the following: if you have A union, if you have 3 of them, then how does it look? Very similar, just a little more complicated. So here is A, here is B, here is C. Then what do? You report A, you report B, you report C, you remove overlaps like a minute ago. But what happens? So here are the overlaps. If this is green, if this is blue, and if this is black, then what? This overlap was subtracted because it was reported twice. This overlap was subtracted because it was reported twice. And this overlap was subtracted because it was reported twice. But what happened? Then this triple overlap was completely removed because that triple overlap was reported 3 times and removed 3 times because triple overlap is everywhere. Reported, 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 removed, removed, removed. So it's removed completely. So it has to be returned once. So it's plus A intersection, B intersection. See, here is the inclusion, exclusion. So kind of builds up on this upper formula. So you subtract intersection of 2, then you go back and add intersects of 3. By the way, if you have more than 3 sets, it works the same way. You just alternate pluses and minuses. All right, let's see a couple of examples to illustrate this. So 416. I think that I'll just need this one with 2, some example. 416. What do we do there? We are considering again numbers between 1 and 999. I really like this question, and I ask it very often on the exam. Alternative on this one. So question 1. How many are divisible by 3? 2. How many are divisible by 5? Number 3. How many are divisible by 3 or divisible by 5? And number 4, how many are relatively prime? Are relatively prime with 15. This is a very nice problem, I would say, because it's fairly simple, but we need to illustrate that we understand all of this. Part time. The answer is 999 divided by 3, which is 3333. Why is that? Because what are the numbers? So how does that work? We have numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. Who's divisible by 3? 1 and 2 are not 30s. 4, 5 not 60s. 7, 8, 9, 90s. So every third number is divisible by 3. So we just divide it by 3 to get the number of those red ones. So here is 333 of those red ones. So that was easy. Part 2, for 5, the same thing. 999 divided by 4. Oops, it's not divisible. But I can say the following. I can just divide between 995. Why? Because 996, 997, 998, 999, there's nobody there. So when I divide this, it will be what? 199. Of course. Alright, let's say they are blue. I didn't draw them here. Now what? Now, so what happens? Here's what you need to hear carefully. Say divisible by 3 or divisible by 5. So it's, I need a count. Let me call this set A and call this B. So I want the count of A union B. Because those are all the numbers that are divisible by 3 or divisible by 5. But here it is. Is there an overlap? Could the number be divisible by 3 and at the same time divisible by 5? Yes, and that's by 15, 30, so those are numbers divisible by 15. So A intersection B is what? 15, 30, 45, and so on. You know, they are both red and blue. How many of them do I? So generally, if there is overlap, I have to use inclusion, exclusion. So it would be cardinality of A plus cardinality of B minus cardinality of the intersection. And that would be 333 plus 199 and minus, what about intersection? The same thing as for 3 and 5, divide by 15. So 999 divide by 15, actually what? Who's the last number divisible by 15? I think it's 990. Yes. So 990 divisible by 15, what would that be? 330 over 5, which is 66. So that's an overlap. I subtract 66. So that would be 3333 plus 1333, which is 466. And what about 4? 4 is the same trick as a minute ago. How many of them are relatively prime with 15? That means they have no factors joined with 15, that they share with the 15. That means they are neither divisible, not divisible by 3 and not divisible by 5. So that's basically all the others, because these are divisible by either one of them, and by De Morgan's law. Remember our De Morgan's law? It says not divisible by 3 and not 5. That means negation or complement. A union B complement, because that's a complement intersection B complement. So generally here it says not divisible by 3 and not divisible by 5, or it's not divisible by 3 or 5. So this is basically complement of 466, and that would be what? Let's go to here. Part 4, I get 999 minus 466, and that would be 533. So 533 numbers between 1 and 999 are relatively prime with 15. Right, and now one more problem, and that is how you use inclusion-exclusion principle. We also assign this problem quite often. This is 417. I'm not going to write the whole text because it's quite long, but generally here it says that in certain discrete math class, 3 quizzes were given, and there are 30 students, a total 30 students, 417. total 30. And then it says the following. 15 scored well. This 12 is irrelevant. It says 15. So they took quizzes 1, 2, 3. So quiz 1, quiz 2, and quiz 3. So quiz 1, how many scored well? 15. Be careful. 15 doesn't mean here. 15 means all this. So 15, some of them maybe, how they did on quiz 2, it doesn't say. So quiz 1 is all these 4 fields together. The same way quiz 2 is 12, quiz 3 is 18, then quizzes 1 and 2, 7, quizzes 1 and 3 is 11, and quizzes 2 and 3, 8. Quizzes 1, 2, 3 is what? Quizzes 1, 2, 3 is 4. And then they ask the following questions. So here are the questions. How many scored 12 or above on at least one quiz? So did well on at least one quiz. Part 2. How many of them well on quiz 1 and quiz 2, but not on quiz 3? What I like about this problem, how it's designed, part 1 is just the formula. Because on at least, that means what? That's counting of A union B union C. Quiz 1 will call it A, this will be B, this will be C. So that means did well at least one means 1 or 2 or 3 or maybe all, so you know, this is not exclusive or. So what would that be? I have all these. It will be cardinality of A plus cardinality of B plus cardinality of C minus A intersection B minus A intersection C minus B intersection C, and then plus all 3 of them. And luckily I have all 3 numbers. So it's 15 plus 12 plus 18. So that's how many scored well on each individual quiz. Then I subtract the doubles, which are here, minus 7, minus 11, minus 8, and then add the triple, plus 4. When you add all these numbers, you will get 23. By the way, what is that telling you? What happened with those 7 students? So 23 students are here. They scored well on one of the 3, but total is 30. Here are 7 students. 7 students are outside. So if you think of a universe, those 7 students are actually outside of those 3. They didn't score well on any of the quizzes. But anyway, now they ask me the following. They want those that scored well on quizzes 1 and 2, but not on quiz 3. It's this. So how can we get to that field? It shouldn't be complicated, because what? Quizzes 1 and 2, the total is, so if I call this V, and this one here U, then they ask me for the cardinality of U minus V. And what would that be? Total for U, which is 1 and 2, is 7. I need to remove those that scored well on all 3, which is 4. That's 3. So that's the answer to this problem. Thank you.